this is your transformations toolkit, which you did a little bit ago, and I just wanted to make sure that you have a guide in case you wanted one. So this is page 15 of your toolkit book, and it talks about rigid transformations, and then we'll kind of look at the page of notes that you need to do something on. So we'll read this together. Rigid transformations are ways to move an object while not changing its shape or size, namely translations, slides, reflections. You can also think of them as flips, and rotations or turns. Each movement is described below. So a translation slides an object horizontally, side to side, or vertically, up or down, or both. To translate an object, you must describe which direction you will move it and how far it will slide. In the example at right, triangle A is translated 4 units to the right and 3 units up. And where did my pen go? Oh no! Oh well. We can record, oh here it is. We can record that as x plus 4, y plus 3. A reflection flips an object across a line called a line of reflection. To reflect an object, you must describe the line the object will flip across. In the example at right, triangle A is reflected across the x-axis, or the line where y equals 0. So that would be this line here where y always equals 0. A rotation turns an object about a point. To rotate an object, you must choose a point, direction, and angle of rotation. So this is the one where you have to really have the most information. So in the example at right, triangle A is rotated 90 degrees clockwise about the origin. So this one's kind of cool. This is triangle A, and triangle A is rotated 90 degrees clockwise about the origin, which means that we really want to think about this shape as its relationship to the origin. So I want to go over that because we haven't talked about this type of example yet, but you don't always rotate a shape on one of the vertices of the shape. You may rotate it around a point that's not actually a part of the shape. And so here, it's rotating 90 degrees clockwise, so in this direction. And when I think about it, I can see the relationship of this part of the triangle. And look at that, it makes a 90-degree angle when I kind of connect those to the origin. So that's a nice way to think about it, is our corresponding parts of your original triangle forming a 90-degree angle, because they should be if you're doing that rotation correctly. So when we look at the page, the toolkit page that I gave you, we've got definitions for each of the transformations. So a definition of a transformation in general is just a movement of a geometric figure in a variety of ways, often on the coordinate plane or a graph. So a translation is a slide. In this example, the triangle in the first and fourth quadrant has been moved or translated to the left and down. So it started here and it moved over and down. And we could describe that as x minus something because it's moving to the left, and y minus something because it's moving down. A reflection is to flip a figure to create a mirror image of itself across a line of symmetry. In this example, the first quadrant parallelogram has been reflected over the y-axis, and it's got these this mirror image or symmetry. A rotation is to turn the figure around a fixed point, and that point doesn't have to be attached to the shape. In this example, the oval has been rotated about the origin, so the relationship of the, what is that called? Ellipse is similar on each of these kind of corners that are formed with the origin. And then the dilation is a stretch, to stretch every length in the entire figure, or you can think of it as scaling. In this figure, the little octagon has been dilated by a factor of 2 to create the bigger octagon. They still share one vertex, but that won't always happen. This will only happen if a point is at 0, 0. If you scale something outside of a coordinate plane, then of course the effect is just to stretch each of the sides by that factor. But when you do it on a coordinate plane, we really want to think about what are the points. If I've got the points -3, -2, 2, 1, and 3, 1, making a triangle, and I want to scale it by a factor of 2. My new points for this will be -6, -4, 4, 2, and 6, 2. So we want to make sure each of the coordinates has been multiplied by the same factor, and then we'll plot those new coordinates. And so your shape should actually expand in a way that looks like one is inside of the other, kind of like that. The first 3 transformations are called rigid transformations, but the last one is not. So why do you think they have that name? Remember we talked about in class, rigid means staying the same. And they're congruent. They're always the same exact size. They are congruent after transformations with translations, rotations, and they are the shapes, and reflections. So on the back of the sheet it says draw and transform the shape according to the direction, so I'll walk you through that in a separate video. Actually, I'll just do it on this video. Okay, so where does it land? On the graph below, plot and label the points. A is -5, 0. B is -5, 3. C is -1, 0. This is -1, C. Connect the dots to make a triangle. So here's our triangle. Transform the triangle according to these directions. Draw each intermediate step on the graph. So translate 4 units right and 2 units up. So 4 units right means each shape is going, or each vertex is going to move 1, 2, 3, 4. So this will be my new C. And then from -5, this will be my new A. And 2 units up means that I need to still go, oops, this isn't my new C. This is my new C. This is my new A, and this has a height of 3, so 1, 2, 3. This is my new B. So this is step 2, this is A, and then I'm going to reflect over the x-axis, so that means this line, I want to reflect over the line where y equals 0. So if this is, I'm just going to write these points, this is -1, 2. That's going to reflect over here, and it's going to be still on the line -1, but my y value will become -2. It's going to be 2 away in the opposite direction. This point here, which was 3, 2, will still be, the x value will still be the same, 3, but the y value will change and be the opposite. It'll be -2. And then here, this value was -1, 5. So my y value is going to be the same, but it's going to be the opposite. I'm sorry, the x value will still be the same, but it'll be the opposite y value. So I've got, this is my B, my A, and my C. And when I connect those, it looks like this. So this is part B. And then C, rotate counterclockwise 90 degrees about the point 3, -2. So here's my point 3, -2. And I want to go counterclockwise. So I want to go this way, counterclockwise 90 degrees. So that means that this line right here, that longest side or height of my triangle, which is 1, 2, 3, 4 units, is going to rotate 90 degrees this way and be kind of vertical now. So that's 1, 2, 3, 4 units. 1, 2, 3, I'm not sure. 1, 2, 3, 4. Oh yeah, it's right here. Sorry. So this is my new A, and then the length of this other base of the triangle is 1, 2, 3. So I'm going to go over 3. 1, 2, 3. 1, 2, 3. I guess this is it. B, and then C, of course, stays the same. So that should be my third one. And so the question is, what are the vertices of the final transform? So A is 3, -6. B is 5. Is that right? 6. Sorry. 6, -6. And C is the same, 3, -2. Could you have used different steps to get the triangle into the same position? Well, we could have certainly translated first and then done some rotation here without going over or reflecting. Let's see. Sorry, this was the original. I think ultimately the answer is yes, you can go any different way. You could bounce around the coordinate plane to end up at your final destination. There's probably a most efficient way, but that can take some playing around with to think about. So that is the end.